Good morning, everyone. Hope that you are having a good start to your Monday. We have our next exam tomorrow. As is the case, or as is what I've offered previously, I stand by. If you would like to switch modalities, I need you to contact me. If you were an in-person exam taker and now want to take it online, please contact me. Um, and if you were an online and want to take it in person, let me know. So today I'm going to be reviewing what will be on your exam number 3 tomorrow. Um, just like the previous exams, you have 1 hour to complete the exam, um, or 60 minutes to complete the exam, unless there's any sort of accommodation, in which case you have the added time. Um, as soon as I think, hopefully before your class on Wednesday, I'll have the exam grades posted. There is more content that I've already posted for Wednesday's class, so the pre-recorded lecture is already up. So actually, let me go ahead and be jotting these things down. Display settings, duplicate slideshow. So there we go. So first things first, we've got exam 3 tomorrow. Um, then 60 minutes, 30 questions, 20 of newer stuff, 10 older stuff. That older stuff is exam 2 content. Then add to that, this can replace, or let me rephrase that. This is worth 15% of your grade and can put this on another item. Um, can replace your exam 2 score. So if you didn't do as well as you wanted on exam number 2, this is an opportunity to bring that up. Now, um, another thing, if you are an in-person test taker, I need you to fill out the Scantron completely. That means name, and I've got name, ID, first page, basically follow the first page of the booklet. And it's stapled, so it's not like a book, but first page of exam booklet has the details on what I need you to put on there. If you do not do that, it makes it very difficult to assure that you get the grade that you earned. So please be aware of that and thoughtful of that. Now, with that in mind, I'm going to go ahead and um, start going through some of the exam and sort of reviewing for the exam. But does anyone have any questions before I do that? If you have any questions, please feel free to add them to the chat. Otherwise, um, um, otherwise I'll proceed. And here we have. Oh yes, you'll be able to use the 3x5 index card on all your exams, including the final. One index card though, for the final exam. So please don't plan on saying, "Oh, well, I'm just going to consult. I'm going to staple them all together." No, just use one. And Wednesday, I will be available for office hours during our regularly scheduled class, and I'll review as much or as little as you want on that day, and then the same thing goes on Thursday. So, oh, sorry, I'm bouncing around a little bit here. There. That's what I do. Um, those. Okay, cool. So now begin drawing, ready. So I want to see chat function, move that over here. Okay, so things to think about on this exam is to think about visuals of the states of matter. And please add to the chat if you are not seeing any written text appear on your screen. I believe that you should be. Actually, could somebody confirm with a Y or an N that they do see red text that I'm writing? Okay, great. Thank you very much. Um, the visuals of the different states of matter. If you remember, we looked at a glass of water. And then with that glass of water, we looked at it changing phase and changing states. So this glass of water is a liquid, and then ice for a solid, and then transitioning to vapor or water vapor as your gas. Then we also looked at it in terms of like kind of molecular or the kind of this was our macro level where you saw the ice cube and then you saw the steam, the water vapor. We also looked at the the kind of molecular level where the ice cube, the solid, was all these balls that were representing different molecules. They're just super packed tightly. The water vapor where it was, they're bouncing all around and there's distance between them. And then the liquid where it was, yeah, they were close in proximity or they were closer in proximity. So these molecules were farther from one another than the solid ice, but they were closer than the water vapor. And all of this was to illustrate what are known as intermolecular forces. Intermolecular forces as opposed to intramolecular forces. Now, intramolecular forces are the bonded atoms. So what I always like to do is draw a pair of different molecules. So I will first draw methanol, C, H, H, O, H, and then H again. And then that's one molecule. Now, these intramolecular forces are now in yellow. So the bonds between the individual atoms, where electrons are being shared between one another, those are intramolecular forces. Whereas intermolecular forces look a little bit more like this. Okay, we've got our separate molecule. Actually, you know what I'm going to do is I'm going to go ahead and illustrate that both of these molecules independently have intramolecular forces. Dun, dun, dun. But then this dotted line is going to represent the intermolecular forces. I always like to use the analogy of the interstate connects states to one another. Intermolecular forces connect, well, molecules to one another. Now, this specific intermolecular force that I'm highlighting here would be hydrogen bonding. Our intermolecular forces, they have, I'm going to go from weakest to strongest. Our weakest intermolecular force is known as dispersion forces. Sometimes you'll see these listed as London dispersion forces. Then we have dipole-dipole. Then it's H bonding. And last but not least, ionic bonding. Ionic bonding is an example of an intermolecular force. It is the strongest of your intermolecular forces. Now, this shows the relationship between, or this table here basically shows our weakest intermolecular forces to our strongest intermolecular forces. Um, Intramolecular forces, you could think about those as being typically stronger than intermolecular forces. Um, the type of force that exists between molecules, your intermolecular forces. Now, with that in mind, that has an impact on our different states of matter. Between water vapor, a glass of water, and ice, you have your strongest intermolecular forces within ice. Now, with that said, it's all hydrogen bonding here, but they're strongest in ice. Now, what that's going to lead to is, well, these have different kind of presences. For example, ice is going to have a fixed shape and volume. Water vapor is going to be unfixed or no fixed shape and volume. A glass of water, or sorry, water in its liquid form is going to have a fixed volume, but no fixed shape. Okay. Now, when we go from there, what separates these things? Liquid water, solid ice, and water vapor, you have those different transitions. So a solid goes to a liquid, goes to a gas. Well, this is melting. This is vaporizing. Then to go from a solid to a gas, that is sublimation. Now to go back from a gas to a solid, that's a process known as deposition. To go from a gas to a liquid is condensation. And then to go from a liquid to a solid, that is, so condensation goes backwards. This is liquid to a gas is freezing. Now, when we talk about these different states of matter, one of the states of matter that we talked about quite a bit was this one right here, gases, because we talked about gas laws. One gas law, known as the ideal gas law, is PV equals nRT. Pressure times volume is equal to number of moles times R times T. R is a value that I will provide you with. This is the ideal gas constant, or simply known as the gas constant. but this shows the relationship between different gases and the volume that they occupy at different temperatures and under different pressures. So if I were to say that you had 3.6 moles of a gas and the temperature was 299 Kelvin, the pressure, so I'll go with N, T, pressure was 4.6 atmospheres. What is the volume that this gas occupies? Now, your units for volume are going to be in liters. Temperature, when it comes to gas laws, absolutely must be in Kelvin. The reason for that is because whenever you use gas laws, you want to use Kelvin because Kelvin is an absolute scale. Kelvin will be 0 to infinity. It will never be negative. Kelvin will never be negative because then you kind of get into this abstract space where it's like, well, what could it possibly be? Because there's physicists that they study absolute zero and attaining or getting to absolute zero. Now, if we were to do this sort of calculation, what we would need to do is take this equation right here and basically rearrange it. We'd have to say V is equal to nRT over P. How did we get that? Well, we took this equation and we just divided each side by P. When we divide the left side by P, pressure gets canceled out because it's on the numerator and the denominator. On the right-hand side, well, we've got number of moles times our R value times T divided by P. Is R something that we need to have? It is. I will provide you with that. And sometimes it will be provided as 0.0821 or sometimes 0.08205. But we plug all that in, 3.6 times 0.0821 times temperature is 299 divided by our pressure, which is 4.6. And I will plug this in to my calculator. 3.6 times 0.0821 times 299. And again, that R value, that would be provided in the problem. Or that would be on the front page that says, like, here's the exact R value to use. 4.6. The rest of these numbers, they're a part of the problem itself. They're a part of the question. And so for this case, the volume would be something like 20.81. Now, in the event that you use Celsius instead, in the event that the question said the temperature is 22 degrees Celsius and you plug that in, your number is going to be pretty drastically different. So if it was 26, I'd plug in that. I'd say 3.6 times 0.0821 times 26 divided by 4.6, and I get 1.67. So this 1.67 number that I've just written out, where did that come from? Well, that came from this alternate scenario where you use temperature in degrees Celsius, not Kelvin. And so that's why I just want to stress to you how drastically different your result can be in the event that the question gives you the answer or gives you the temperature in degrees Celsius as opposed to Kelvin. So that's why I scribbled that out now. Okay, so gas laws are an important part of this exam because they're exam 2 stuff. In addition to that, one of the things that we talked about this semester, and man, oh man, the semester blows by. We talked about polarity of molecules. For instance, we talked about NH3. Well, NH3 and H2O, Those are both really good molecules that I want you to basically be able to kind of draw them in your head. NH3 looks a little like this. You know, if you're thinking, oh, well, I need like four molecules to, or, are there molecules that you expect us to know? Um, I'm not going to say expect. Let me rephrase that. Are there molecules that will be valuable for us to know how to draw, as opposed to looking at the periodic table and piecing it together? NH3 is a good one. I would say NH3, H2O, and excuse me, CH4. If you can recall and draw those, you're going to be in really good shape. The reason that those are going to be valuable is because one, they show you the difference between lone pairs of electrons. Here we have NH3 and CH4 and H2O. These two molecules have lone pairs of electrons, LPs. NH3 has one LP. H2O has two LPs. CH4. Ooh, CH4 has zero lone pairs. Now, what makes them also stand out from one another is that NH3 and H2O are both polar. CH4 is nonpolar. These molecules also have different geometries from one another. Now, NH3 and H2O as not as polar molecules, these two will mix because like dissolves like. It's almost like likes like. It's kind of a tongue twister and confusing, but those two will mix really well together. CH4, if you added CH4 to H2O, it's not going to mix. That will not dissolve well, or that will not go into solution particularly well. Same thing goes if you put CH4 in NH3. Also, it's not going to mix well. But if you put NH3 into H2O or H2O into NH3, those two solutions will mix really well together because the principle of like dissolves like. A nonpolar substance will go into another nonpolar substance. A polar substance will go into another polar substance. Now, we've got two options here, P or NP. Tell me what NAF will go into. Is it going to go into P or NP better? Add it to the chat. And I'll give you a little bit of a hint. NH or Na4 is an ionic compound. DDA, you're absolutely right. NAF goes into a polar solution perfectly, like a dream. If you added NAF into something like CH4 or another non-polar solvent, nope, because Na4 is ionic. Now, what about something like, let me remove this. I'll go with this, NaOH. What's that going to go into well? Is that going to go into a polar or a non-polar solvent well? You're absolutely right, Didier. It's going to go into a polar solvent because, again, NaOH is ionic. Okay, so lots of that is the review sort of content. Now I'm going to, well, NaOH will hydrogen bond. It will help out with hydrogen bonding. You're absolutely right. Um, then let's see. The next thing that I wanted to talk about that we went into last week was acids and bases. I gave you some definitions and some ideas of acids and bases. Um, if I showed you a compound, I'm going to use A kind of as a placeholder. If I had HA, versus AOH. I'm going to use these kind of as like your placeholders almost, your models. This substance right here will dissociate into H plus and A minus. This substance right here will dissociate into A plus and OH minus. This is an example of a base. This is an example of an acid. Now, we have this one as an example of an acid because when this dissociates and dissolves, it makes this right here. It makes a hydrogen ion. Hydrogen ions, those will cause the pH to go down. So if you were able to, you know, Harry Potter style, get a magic wand and go, I didn't really watch Harry Potter or read them. Magicus acidus, then you would make H plus appear in a solution, and then that would cause the pH to go down to become acidic. Now, if you had a bunch of hydroxide ion concentrations, or if you caused the hydroxide ion solution, or sorry, hydroxide ions to appear, then you would make a solution more basic. Add to the chat, anyone, what is the range of the pH scale? Numerical range. Sorry about that. 0 to 14. You're absolutely right. Now, give me a number, sorry, that corresponds to, give me I'm doing a pH test and I see an acidic pH. What number would I expect to see? Just give me any number that would indicate an acidic solution. Perfect. Fantastic, DDA. Great job, Landon. Those are both indicating of an acidic solution. Now give me a basic pH. 7 is more basic, yes. It's a relative scale, but I would go ahead and classify 7 as neutral. So I wouldn't say 7 is acidic or it's basic. I would say it's neutral. 8, however, yes, you're absolutely right. 8 is a basic pH. So, and I am going to split hairs on this one. Um, and just to stress that this is a relative scale. And I mean a relative scale as opposed to an absolute scale. A relative scale meaning that 7.001, how would you classify that pH? That is acidic, or that is, sorry, basic. 6.99999999999. Draw a more definitive line there. That is acidic. 7.0, neutral. 7.00000 is neutral. So it's important to be able to kind of recall and know those. Now, there are some important properties of acids and bases. One thing about a base that's important, I mentioned this, and could anyone remember or recall when you touch a base, what's the sensation or what's the feeling? If you've spilled a basic solution on your hand, it's going to feel kind of slippery. Can it produce a burn on your skin? It absolutely can. So you got to be cautious of that. But this is going to feel slippery. Okay. Now, another thing when it comes to pH is how to calculate pH. The pH scale is a log scale. And one thing that I want you to recognize is whenever you're asked about a pH scale, it's all about, in these brackets, it's all about the hydrogen ions. I'm going to add two things. These brackets right here indicate molar concentration. If you had a solution that was zero or hydrogen ion concentration, so that bracket or those brackets surrounding an H plus, and let's say your solution was it had hydrogen ions with a concentration of 0.01 molar. We did a discussion or we talked about molarity. That would mean you have 0.01 moles of hydrogen ions. And what would I put underneath that line right there? This is all about molarity. So the capital M. Moles per what? Liters. Absolutely. This would be 1 liter of solution. So if I had a solution and I said, hey, you've got this solution where the hydrogen ion concentration is this. What's the pH? And another way of looking at this, another way of thinking about this is this right here is the same as 1.0 times 10 to the 1, 2, negative 2. Give me a y or an n if you follow this relationship right here. Okay? Because all that I'm doing is taking full notation to scientific notation. But now with that in mind, tell me what the pH of this solution is. Perfect. So DDA, you're absolutely right. This solution would have a pH of 2. Now, with that in mind, there's basically two different ways that you can approach this. You can say, how many places did I move the decimal? Well, I moved the decimal 2 places. Okay, there we go. That log relationship tells me my pH is 2. So, um, that's just kind of one of the things to keep in mind. Then what we have is when it comes to acids and bases, we have, excuse me, I believe we did acids and bases. That was our discussion on Friday. Yeah. Okay. It could have been Thursday. I can't remember exactly. Let me check the PowerPoint where I saw it. If that's what you're looking for, acids and bases. Look at the day 13 slide deck. Okay. Let's see. Solutions. We talked about molarity on 13, which I believe was Thursday. And then Friday, day 14. The slide deck was titled Day 14, Acids and Bases and pH. Yes, it was on Friday. So I'll show you the PowerPoint slide if you want to reference that file. And then you can kind of scrub through the YouTube video to see precisely where it was, timestamp wise. I'm going to change my screen in just a second to show that file. So acids and bases and pH. And for the calculation, slide number 12 and 13, we talked about a specific example there. Yeah. So there you go. Slide 12 and 13 from the day 14 slide deck, which was the Friday slide deck. Oh, I haven't posted that one yet? Gregory, I'm sorry about that. I will get that posted today. And likewise, I will post today's recording. Sorry about that. Um, Thank you for bringing that to my attention, though. Okay. So, okay. Um, okay. Actually, five of the videos. Okay. So, yeah, we talked about acids and bases. And when it comes to acids and bases, we have two classifications. We have strong acids and we have weak acids. Now, when it comes to strong and weak acids, there are just a couple of examples of um, strong acids and strong bases. So, your strong acids, there's a limited list of them. And I'm going to write those down in just 1 second. Okay, your are strong acids are HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. Your weak acids, all other acids. Everything that is not a strong acid is a weak acid. Now, strong bases. I'm going to switch to a different color so I can kind of keep this straight. Strong bases. Your strong bases, well, are LiOH, NaOH, KOH, CaOH2, SROH. Sorry, that's supposed to be an S, not a B. Looks like a B. SROH2 and BaOH2. Weak bases are all others. These are the only definite strong acids or bases? No. These are, sorry, or is this just an example for a general list of them? No, this is it. These are the only strong acids, the only strong bases. So in the event that you're looking at this and you're like, "Oh, should I know those?" Yeah, you should. If I were to mention, "Oh, well, NH3. NH3 is a base." How would you classify NH3 as a base? Strong or weak? Weak. Yeah, because it's not one of the strong bases. Now, is there anything that somebody notices about all of the strong bases? What do they all have in common? Not just hydrogen, OH. Absolutely. Now, what's important to recognize about your strong bases is that, yeah, they all do have OH, but this is kind of like um, or actually, is a little bit of a follow-up. Let's say MgOH2. How would you, is that a, would you think that's a base? Let me ask you that. How would you classify it? Weak. Great. Yeah, it is a weak base. Is it a base? Yes, it is. Is it a strong one? No. Why isn't it a strong one? Well, for one, it's not in the list. Now, when it comes to strong and weak bases and strong and weak acids, I'm going to use the strength is because of dissociation. If I were to come up and I said, "Oh, good, I found a new strong acid, and it is HX." And you said, "Well, what's X?" And I was like, "Well, X is a new element, and I'm going to call this xenooxic acid." And I said, "It's a strong acid, and we're going to add it to the list." And you said, "Okay, well, why?" What I would say is because H and X, they separate completely whenever they're in solution. So in solution, you'll find whenever you add HX to water, you find H and X minus. What does that mean you do not find any of? So if they separate as H plus and X minus, what is not there? This means that there is no perfect Didier. Absolutely. There is no HX in solution because they separate completely. It's almost like, um, or in solution, you will never see HX, just like HCl in solution. So let's say that you got some solid HCl and you added it to water. You will see H plus and Cl minus. You will never, ever, ever see HCl in water or in solution. I always kind of think about it as like, if you know someone who wears cargo shorts every day, you'll never see them wearing pants because they only wear cargo shorts. That's it. That's they are strongly drawn to cargo shorts. They never wear like sweatpants or anything like that. Okay. Now if I were to show you a different acid like if I had HF, tell me how you'd classify that acid. It's a weak acid. So in solution, what will you see? I'll give you a hint. There are three things that you will see if you take HF and you throw it into water. What are those three things? Perfect. You'll see HF together. You'll see F by itself. And you'll say H by itself. And you might think, but how? Well, you're not throwing one single molecule of HF in there. You're throwing thousands of them, millions of them. You're throwing moles of them. Okay. So acids and bases and their strengths is a very important part of this exam. Then we also talked about molar mass. If you were to see something like SrOH2, exactly. How many oxygens are here? Okay. Now I've got 50 molecules of SrOH2. How many molecules? Or sorry, how many oxygens are there? 100. Perfect. How many Sr are there? Perfect. Now, this OH, that sticks together. What is OH minus an example of? I'll give you a hint. It starts with a P. It's not polar. OH minus is an example of a polyatomic ion. Okay. Now, if I were to ask you, what is the molar mass of SrOH2? Well, I'd have to look at the periodic table and I'd have to say, well, what is the mass of Sr? Let's say that Sr had a mass of, let's call it 87.8. Oxygen, I'm going to go ahead and say is 16, and hydrogen, I'm going to say is 1. My molar mass of this would be, let's see, 2 oxygens, so that's going to be 32, because I'm multiplying that by 2. 1, I'm going to multiply that by 2, so I'm looking at 32 plus 2 plus 87.8. So we are looking at a grand total of 34, 87.8 plus 34 equals, let's see, 121.8. And that is grams per mole. Now, that is a base because it has hydroxide. Is SrOH a strong base? Well, is it? It is an example of a strong base because it's in my list of strong bases. Now, what type of reaction exists whenever I have an acid plus a base? I'll give you a hint. An acidic pH plus a basic pH ends up in the middle, making a what type of pH? Neutral. So this is known as a neutralization reaction. Now, this type of neutralization reaction, an acid and a base, a neutralization reaction will always make 2 things. One of them is salt. And the other is H2O. Now, when it comes to salt, I'm using that term in the chemical context. Every single acid and base reaction will not make NaCl. NaCl is an example of a salt. If we had HCl as a strong acid and SrOH2 as our base, we would have this hydrogen ion and these hydroxide ions that they will pair up to make H2O. Can you tell me what's the other product that I'm going to make? Add that to the chat. And don't worry about, well, yeah. If H and OH are kind of done for, all that I have left is Sr and Cl. So I'm going to make SrCl. But one thing that you have to keep in mind is, does anyone know the charge on Sr, or can you deduce what the charge of Sr is based on knowing the charge of hydroxide, which is -1, and this formula, SrOH2? What's the charge of Sr? It's positive, but what? Positive what? Based on this right here, do we see a subscript around OH? We do. That OH is in the parentheses, and we got a 2 outside of there. So that means that we have actually -2 because there's 2 hydroxides. So Sr has to therefore be +2. So what that means is our Sr It actually has to, or our product has to be SrCl2. That is an example of a salt. And sorry, my scribbling over that might have thrown your answering off of there. So I apologize for that. Um, but that is an example. You're going to make salt and water. SrCl2 is the example of a salt in this reaction. Now, another thing that we talked about was balancing a chemical reaction. When you balance a chemical reaction, you have to balance the number of atoms of each type, but do you have to balance the number of molecules? If you have molecule A react with molecule B, that's two reactants. Do you have to have two products? Y or N to the chat. Do two reactants have to make two products? No. Two reactants can come together to make one product. Two reactants can make three products. One reactant, A, could decompose into B plus C, just as a little bit of a model. Now, when we have a chemical reaction like CH4 plus O2, this is a combustion reaction, and this will always produce CO2 plus H2O. There's our balanced chemical or our unbalanced chemical reaction. How do we approach this? Now, the questions that you guys are going to be given, answer options, are going to, I want you to use them. Let's say that this question was, what is the coefficient for CO2 when balanced? Let's say that you had answer options of 0.5, 1, 1.5, 2, and then let's go with 3. So these are our answer options. We've got 0.5, 1, 1.5. Well, I keep doing that same mistake. Sorry about that, everyone. 0.5, 1, 1.5, 2, and 3. Now, are there any answer options that we can immediately eliminate? Tell me in the chat. Oh, and actually, I'll go with F just for the heck of it. Can we eliminate some of these right off the bat as our coefficient for CO2? Okay, we can eliminate A, yeah, A and C, because those are not whole numbers, and you're absolutely right, F. Because if it was 0, that would mean no CO2 is going to be produced. So we're left with 1, 2, and 3. Now, considering that, if we look at answer option B, that says 1. 1 in front of CO2. Our reaction as it stands right now, is it balanced? It's not. But does that mean we can rule out 1 as the answer option? No, but it kind of makes me think that we probably will. But based on this, well, no, we can't. Okay, so let's go ahead and work through this. And then we'll kind of pivot and say, play around with it. Okay, the first thing is we want to find an atom to track and see if it's balanced or not. Are our carbons balanced? Yeah, we've got one carbon on each side of the reaction. Balanced, done. The next element is hydrogen. Are our hydrogens balanced? They're not. How are we going to balance them? We've got 4 right here, and then we've got 2 right here. Easiest thing that we can do is put a 2 coefficient in front of that H2O. Does that balance our hydrogens? It does actually, because hydrogen is only found in those 2 molecules. Now, I was talking with one of your classmates earlier today and said that balancing a chemical reaction is a lot like playing the game Whack-A-Mole, where you fix one thing, then you produce another problem after you fix that. Now, when we put this 2 coefficient in front of the H2O, what did that mean for everything else in that molecule? Well, that means we doubled everything else. So now tell me, how many oxygens do we have on the reactant side of this equation? On the reactant side, oxygens. We've got 2 oxygens. Tell me how many oxygens we have on our product side. On our product side, we've got 2 oxygens here, and then we've got 1, but this 2 impacts that. So now we have 4 on the product side. Okay, so, well, huh. If we put a 2 coefficient in front of that 2, are we balanced? Are our oxygens balanced? I'm sorry. Yeah, that 2 causes this to go up to 4, so our oxygens are balanced. Oh, but did that throw a wrench into anything else? No. Why not? Well, the reason why not is because this 2 only applies to this oxygen. That's the only element within that. And so then we basically just have to say C, H, and O. Are our carbons balanced? We've got 1 and 1. Check. Are our hydrogens balanced? We've got 4. We've got 4. Check. Oxygens. We've got 4. Then we've got 2. And then we've got 4. Check. We're balanced. We're golden. So this question, what's our coefficient for CO2 when this equation is balanced? Oh, it's actually 1 because we didn't have to do anything. Now, that's a tempting answer to eliminate just because it's like, well, it's not balanced, so we have to change it. No, you don't. So just be kind of cautious and thoughtful of that. Now, when it comes to balancing chemical reactions, it's all about ratios. One of the things that we talked about was stoichiometry. Stoichiometry can be summed up with, um, I like the cheese sandwich example, also the, what was it? The hot dogs plus buns. You get 6 hot dogs in a pack, and then you get 8 buns in a pack. To make 1 hot dog, what do you need? Well, you need 1 hot dog and 1 bun. But when you buy packages, you get 6 and 8 at a time. So how would you do that where you're going to end up with nothing? Well, you'd have to increase the number of franks that you get, and then you're going to have to increase the number of bags of hot dog buns that you get. And you keep going back and forth until you have the ideal ratio. And I think that if I remember correctly, it was you would get 8 packages of franks and 6 packs of buns. And you would end up with 54 hot dogs. All right. Now, that's all stoichiometry right there. We also talked about solutions. And if you were to make a solution of, let's say, NaCl, NaCl has a molar mass of 58.4 grams per mole. And if you're thinking, where did that number come from? Well, that number came from the periodic table. If you were to make a 1 liter solution, so that's your volume, with a concentration of 1 molar, how much NaCl would you need to make that solution? Exactly. 58.4. Let's say that you made zero point 0.5 liters of a 1 molar solution. What mass of NaCl would you need? How much NaCl do you need? Half. So you do 58.4, you'd end up with 29.2 grams. So to make a zero point 0.5 liter solution, your volume went down, your concentration stayed the same. Both of these solutions will have 1 mole NaCl per 1 liter of solution. Now, if you were to, let's think about if you made this solution and you started heating it, what could you tell me about the particles within this solution? Are they going to move more or less? More. Um, do you think that eventually you might get to a point where this vaporizes if you heat it enough? Okay, and what would that vaporization? Oh, wait, there was our word. This vaporization is going to convert this to which state of matter? Gas. Perfect. Um, let's see. Okay. Now, this is pretty much the last thing that I wanted. No, the last thing that I wanted to go over is, um, let's say you had this 1 molar solution of NaCl, and it's 0.5 liters. Um, if I added 0.5 liters of H2O, what's going to happen to the concentration, that bracket there, the bracket, the concentration of NaCl? If I added H2O to this, added 1 liter of this, is this going to go up or is it going to go down? It's going to dilute it, so it's going to go down. Yeah, the concentration will go down. Now, let's say that I had a zero, let's change this a little bit. Um, let's say that I had 0.5 liters of a solution, and let's say that the solution had a hydrogen ion concentration of 1.0 times 10 to the negative third molar. What can you tell me about that solution? There's a couple of things that I'm curious about. If you put your hand in this solution, um, is that the same as putting your hand into a glass of tap water? Y or N? No. Um, which one are you going to notice more quickly? It's acidic. That's exactly what I'm looking for. I agree with that. In addition to describing it as acidic, um, what else can you tell me based on this number right here? Its pH is 3. I like it. Now, you told me, or you guys told me a little bit ago that in this solution that I'm going to label A, solution A, When I added more water to it, my NaCl concentration went down. I agree with that. Totally. Completely true. Now, solution B, I have a hydrogen ion concentration, and to that, I'm going to add zero point 0.5 liters of H2O. Okay. Now, one of the things that I want you to remember is this hydrogen ion. Okay. Yeah, DDA, you're absolutely right. This is neutral. This hydrogen ion concentration, think about that as, well, you've got these hydrogen ions that are floating around by themselves. Um, when I add this H2O to this solution right here, I am adding a bunch of this molecule, this H2O, that's like intact. Add a Y or an N to indicate, yeah, I understand that. This is neutral water. Okay. I'm adding H2O as one complete thing. What will that do to the hydrogen ion concentration? Is that hydrogen ion concentration going to go up or is it going to go down? It's going to go down. You're absolutely right. Why is it going to go down? Well, it's going to go down because I've increased my volume, but have I changed the number of hydrogen ions in that solution? I have not. I've changed the total volume, but I have not changed the hydrogen ion concentration. Okay, so I can give you two answer options, A or B. The new hydrogen ion concentration is, and don't answer yet. Now I'd like you to answer. Is the new hydrogen ion concentration A or is it B? And if you need to, go ahead and convert this from scientific notation to full notation. And, that's actually what I'm going to do. I'm going to take this scientific notation and convert it. 0.01, or wait, no, that would be 0.1, sorry. It's going to be 0.1 molar or 0.00001 molar. And 0.1 molar would be 0.1 per liter. And this would be 0.00001 per 1 liter, 1 liter. Okay, so my question is, what does our new hydrogen ion concentration look like? Does it look like A or does it look like B after the addition of this neutral water? A little bit ago, I was told that the hydrogen ion concentration goes down, and I totally agree with that. Your hydrogen ion concentration goes down from 1.003 or 1.00 times 10 to the minus third, which is the same as 0.001. You're absolutely right, DDA. B, that is our new hydrogen ion concentration. We added more water and we diluted the hydrogen ion concentration. So, with the addition of more water, what did that mean for our pH? Is it neutral? We added more water, which the water was neutral. Okay. But tell me, yes, that's what I was looking for. What is the new pH? The new pH we based on our hydrogen ion concentration, 1.0 times 10 to the negative fifth. That means our new pH equals 5. Does that make sense, DDA? Y or N? Okay. There's some steps here. We had an acidic solution. How acidic was it? Well, it was so acidic that our pH was 3. Well, that pH of 3 is based on a hydrogen ion concentration of 1.0 times 10 to the negative third, which is the same as 0.001 molar. To that solution, so here we go. H plus, H plus. I'm just going to draw 3 hydrogen ions. Here's our solution. It's 500 milliliters. Then we get water, pure water. We add it to there, and then we get a new solution that looks a little bit like this. Our new volume of our solution is 1,000 milliliters. We have 1, 2, and 3 hydrogen ions, but think about this as 3H plus per 500 milliliters. This is 3H plus per 1,000 milliliters. The total volume of our solution went up, but the number of hydrogen ions stayed the exact same. So relatively, I'm going to put this as relatively, this solution is more basic than this one. Because our hydrogen ion concentration, in a relative sense, our hydrogen ion concentration went down because it's the same number of ions in a greater volume. Okay. That's what I've got for your review for this exam. Does anyone have any questions about this exam? Okay. I'm going to go ahead and stop my share. I'm going to go ahead and stop my recording.